at NASA when I was 16. Started as an intern and came up in all sorts of different areas. So you want, this engineering is a blast. So please pay attention and let's do good science, good engineering projects this year. So this is a workshop designed to help you with your engineering goal statement and to understand engineering projects. If you could flip the screen, please. And if you feel the need, interrupt me at any time. I don't mind. Questions? Could you please change the slide? There we go. So the purpose of this is to try to help you guys understand the engineering design process as compared to the scientific process. If we can move to the next slide, please. And so the outline for this talk is we're going to go through what is the difference between science and engineering design processes, 7 steps of the engineering design process with examples on each step, pitfalls that you should avoid as you're putting together your projects, and then a quick summary at the end. So if we can move the slide, please. And again, so if you want to talk about the difference between science and engineering, science is a search for fundamental understanding. So right now I'm working on the Viper Lunar Rover at NASA Ames, and we want to understand if there is water contained in the permanently shaded regions at the poles of the moon. But there's also engineering involved in this project, and that's the application of scientific principles to satisfy human needs. And in the case of the Viper Lunar Rover, it is the engineering processes to put together the equipment needed to carry the science equipment so the scientists can get their information from the moon. So these are both very, very creative processes and a lot of problem solving that goes on into this. If you could pop the slide. And so science and engineering. For science, you ask the question why? Is there water in the poles, captured in the poles of the moon that we could use? Go through all of the different equipment, understanding of how to get it, and come out with knowledge at the other end. If you can go with one more slide. But with engineering, you have to know your need. You have to understand the state of the art in science and technology. You use the design process in order to put together a prototype, which then creates a specification that enables you to produce, commercialize a equipment. So they both come out with different results in the end. Knowledge versus actual equipment, prototyping something that you can sell. If you can, next slide. And so we'll first talk about how you define the need, how you establish your criteria and constraints, research various, what's been done in the past, what are the alternative approaches that you could do to do this project, and how are you going to test it once you put it together? Then you construct the prototype, you test it against the criteria you established in 2 using the test plan you put together in 3, and then you do a failure analysis. I'm sure it isn't going to work the first time, so you're going to have to tweak it and retest it, and then you document what you've done. So if we move on. So the step 1 is record everything in your project notebook. And this is a complete record with all of your key decisions, good drawings of what you're going to put together, and if it's software like flowcharts are very, very helpful. Put together a list of your high-level test plans at the beginning. You'll flush them out more as you go through your project. Eventually, you'll get results from your testing, and then take the results and come to conclusions about whether or not your project met the criterion that you decided upon at the beginning. And it's always good to have a lessons learned section. What did I actually, what beyond the engineering project did I learn about the process? So this is shown as a paper notebook. These days there are established online lab notebooks. I took a look the other day and I saw like 7 or 8 free lab notebooks online. The main thing is that they allow you to keep a temporal, your results across time. You can't go back and change previous results based on new information. That's a really important thing to maintain your line of thought as you go through the project. So, whether you use paper or one of these online approved methodologies, make sure you have a really good test notebook. Next one, define a need. Especially for an engineering project, you really have to have a customer for the project, somebody who really wants what you want to sell. And so, oftentimes somebody says, I want an iPhone, but I want it to have more memory. I want it to also serve as, a robot controller. Or maybe I want to miniaturize some robot. It needs to be a lot lighter for me to get it to these places. And so, in a lot of cases, so when you get to one of these, you get to an engineering goal statement, where you're talking about the design and construction of some engineering concept for some stated end user to do some function. So, for instance, with Viper, the design and construction of a Lunar Rover for mission operations to take science data on the moon. That would be something for my project at work. And these projects have got to have technical content. You can't just, I've seen things like people building rolling pins that really didn't have any technical content whatsoever. So if we move on to the next page, and we'll get back to the engineering goal statement in a little bit, but how do you generate your ideas? Find something you're passionate about. What are your interests? Is there something you need to do sports better? Is there something with the environment that you think that you can make a difference about? Listening to other people's complaints. This is one of my favorite ones. If I could sit down with a set of end users and listen to them whine and groan about how bad some tool is, then that gives me a lot of ideas on how to fix it, make something better. You can think about what cool improvements you could do on something. There's other things that you can do. There's online aptitude tests that you can use to kind of steer where you might be able to put your interest. So if we move to the next slide. So here's a set of links that I provided where you can get ideas from. Your teachers have this presentation, so don't worry about copying this down. They've got it directly. But some are, Science Buddy sites, How Stuff Works. There's a bunch of education-oriented websites. I'm really personally interested in the area of nanotechnology. I'm hoping to see more science fair projects in that area. But there's also the research sites of all of the engineering societies. They're a good place to look for, papers, ideas of modern interest. So if we move on. So let's go through the engineering goal statement exercise. And I think a lot of you got an engineering goal statement paper. I'm not sure if all of you did. That's okay. But what we're gonna do is we're going to construct engineering goals from that template. And so the template is the design and construction of some project for some user to function. And so in this particular case, we're gonna plug in project user and function. So the design and construction of a solar-powered scooter for children to zip around the block. Woohoo, simple, okay? So it's a simple plug-in of the project, the user, and the function into the goal statement. And once again, I'm gonna say you need technical content, and this one has plenty. Solar energy, energy storage, motor torque, physical construction, the gear ratios of the bike, braking systems. So there's all sorts of different things that this has technical content in. So if we can move on. All right, so this is a copy of the piece of paper that many of you have in your laps. And if I could get a volunteer to pick the first project and find the associated user and function and tell me, plug it into the design goal template. Can I have a volunteer, please? Woohoo, you. The first one, please. So the design and construction of a.
The design and construction of a hose-powered hubcap cleaner for car washers to clean small crevices in hubcaps.
Perfect, excellent, thank you. That is exactly the way these the goal statements are written. Very simple, straightforward. Can I have a volunteer to do the second one, please? Yes, you.
Electromagnetic.
The whole statement, please.
The design and construction of the electromagnetic padlock opened by a specific light sequence for a businessman with a laser pointer to do block valuables without carrying the key.
Beautiful, thank you so much, awesome. Someone over here, can somebody over here do the third one? Yeah, you. The whole thing, please. Perfect, and isn't that one that's always being used these days? I mean, wireless technology to keep an eye on your meat while you're doing long barbecues. Okay, back over here, somewhere over here. Oh, sure, you.
The design and construction of a spoken English input to Mandarin text output translator for English-speaking tourists and businessmen to communicate with Mandarin speakers.
Beautiful, awesome. All right, next one. Did I see you raise your hand partially? Yes, I did. Why did you do it? Yes, you in the yellow shirt right here. Yeah, you. Fantastic, excellent, thank you. And the last one, please. Yes, you.
The design and construction of a soft heater for people who are cold feet to automatically turn on
Perfect, beautiful. And you would be surprised at how many automated sock heaters I've gotten in science fair now. I'm also a judge at science fair, so I get to see the beautiful creativity that you guys produce. Okay, awesome. So when you are thinking about your goal statements over the weekend and turning them in on Monday, honestly, this is what I'm looking for, something very simple and straightforward, okay? So keep it this easy. Makes it really clear to me what you're doing if you use this template. All right, next page, please. All right, so step number 2, figure out your criteria and your constraints. And so the design criteria are requirements you specify that your design that will be used to make decisions about how to build the product. And so here's a picture. This is the Viper Lunar Rover. Its construction and design is based on the environment that it's going to be in. It has to have enough battery and solar electric panels on it to be able to charge up and take it into permanently shaded regions where it can drill and get back out so it can charge back up again. So that affects that affects the functions of the instrument. It also has, as it's drilling, it's got instruments, spectroscopes, to be able to determine the composition of the dirt that it's bringing up, and hopefully find water and other volatiles. And so those sorts of things specify a lot about the rover. So it basically sets the size, because we have to fit on the rocket. So that sets a limit on the mass. The appearance is dictated by the solar panels, basically, and the fact that you've got to protect all of this equipment inside against the cold and the heat on the moon. It's from like 90 Kelvin to 240 Kelvin. So it's a wide range of temperatures that it's going through. The physical features, like the wheel size, is because of the use environment. We're going to be in soil that we have no clue what the composition of that soil is. We've got to guess from the equatorial soils, but we don't know if they're going to be indicative of the soils at the poles. And then of course, you know, so that use environment and performance. So we have to be able to outrun the shadows because we are down at the poles. The sun is coming at an extreme angle, and as it moves, the shadows are moving around and chasing the rover. And so we've got to move it around to avoid the shade and get into these permanently shaded regions. And then there's 2 weeks a month where the sun is out of view. And in those points, we have to go find a safe haven and sit there and charge and be safe so that it can power back up and run again when we are back in Earth communication. So all of these things drive the design of this rover. Anyway, that's the process we're in right now, is designing that rover. All right, next one. Other constraints on every project. Cost. We have a hard cost cap. Time, we have to launch in 2023. That's serious. It drives what you do. And you have similar issues. All right, next one. So let's think about this for a particular solar-powered scooter, that guy that we talked about at the beginning. And let's say the requirements on it are that it has to transport up to a 35-kilogram rider. It has to have a minimum speed of 8 kilometers per hour on a level surface. It has to travel at least through 10 meters of shade. The material cost, let's say it has to be no more than $100, whatever. And the testing has to be complete by February 28th. And you back out that time. When's the science fair? When's your project due? How much time do you need to research it? How much time do you need to prototype it? You back that up and figure out what you have to do in each phase of your project. Okay, so if we move on. So step number 3, do some research. What have other people done? For us, we're talking a lot with the folks at JPL who run the Mars rovers. And they're giving us a lot of fantastic advice. So you can look it up. Google Scholar is a fantastic way to find what else has been done in the particular area you're looking into. And that way you can find good alternatives that may be cheaper or faster or better technology, lighter technology. And then you also create that test plan. So things that you have those criteria on has to be able to hold 35 kilograms. Well, that's an easy test, put 35 kilograms on it, right? So really easy ways that you can create those test plans. All right, next one. All right, so here we are, and it's a test plan. Transport up to a 35 kilogram rider. What did I just say? Put a 35 kilogram weight, at least a 35 kilogram weight on it. Speed of at least 10 kilometers per hour on a level surface. How would you test that? Just yell it out, please. How do you test speed? Yeah, get on it and actually see how fast it can go. How would you measure the speed? That's right, you could tow distance over and the time it did. You could take a radar gun. You know, if you think about it, there's usually several different ways that you can measure something, okay? So think about what the best way is for your particular project. Travels through 10 meters of shade. What would you do? I mean, the answer's already up there, so you could just talk it to me.
Charge the battery?
Yeah, charge the battery so you have a known initial condition. It doesn't make any sense to do this if you start with an initial condition of a flat battery. It just doesn't work. So think about your initial conditions. If we can move on. Yes, some of you will try to incorporate humans in your engineering experiments. And I just want to caution you that anything being done with humans has to be pre-approved. You can't, and that pre-approval period is starting like right now. So if you're going to do this, very carefully read the rules for human participants and fill out and attach the human participant research plan to your engineering application. And unless your project is exempt, and so if we move on to the next slide, you are exempt from these regulations if it's a student-designed invention that does not pose a safety risk, like that scooter, that is only being tested by the student. So if you yourself are the only person testing it, you do not need to go with human regulations. But if you propose that 20 of your closest friends are going to get on this thing and write it to test it for you, that requires a human participation form. So think about how you're going to do your testing. Data, if you can back up, please. Data record analysis projects. If you're going out to some database, pulling it down and doing post-processing of the data, even if it's human-related data, it's usually anonymized. You can do that without an IRB form if it's anonymized. And you can do behavioral observations in unrestricted public settings. So, somebody doing I've seen this where they try to evaluate different garbage can configurations. And so they just sit back and watch. Does somebody use this can or that can, and how? I mean, those sorts of things where you're not forcing anybody to do anything, but you can observe how they interact. Okay, now. And the process has changed this year, thank goodness. There is an online process for submitting your science fair proposals. And so, like I said, you've got this presentation, you don't have to write these links down, but there's a whole series of forms that you have to fill out. There is a particular template for engineering projects that you need to fill out. And that template contains the topics that we've talked about today. An engineering goal statement, please, just that one simple templated line. That's easy. Design criteria and constraints. The project design, flow charts, pictures, drawings, whatever. Circuit drawings, a basic test plan, really basic test plan, and a bibliography. And I bounce so many proposals back because they don't have 5 high-quality references. And I mean complete references. Just don't say Wikipedia, okay? Because I am going to bounce you on that. So full HTMLs of the page that you got the information from. And I like it, there's several standard forms, pick one, Harvard form, I don't care which one it is, but be consistent, high quality reference. And when you've completed your forms this year, you're going to upload them to your particular folder, and there will be instructions on the website on how to do this. Okay, so it's nice, we don't have to mail forms back and forth anymore, yay. All right, next one, minimum quality requirements. There's a lot of forms that come back with a lack of measurable data. It has to be really good. It has to go fast. How do I measure fast? You have to tell it faster than what? Something like 12 kilometers, it must be faster than 12 kilometers an hour. It's too heavy, it can't be too heavy. It has to be no more than a mass of 44 kilograms. High accuracy. What do you mean by that? You have to say something like less than 17 errors per 1,000 samples. Figure out a measure of what's good in your project. Something that you can calculate and say yay or nay. That's what we're looking for. As I said before, an inadequate bibliography. And plagiarized experiments. I do go through and I Google what I see in these applications to see if somebody took a Science Buddy experiment in whole. You can use it as a basis, but you can't just steal it from a website, okay? You have to have original content of your own. And so I do look for plagiarized materials, and I will bounce projects if I find them. Okay, next one. Construct your prototype. All right, this is fun. Build it, put it together. And it is the implementation of all the research you did. This is your favorite implementation, something you think you can build. And it's a proof of the design that you can produce it and that it's suitable for the criteria that you put together. Next one, please. Test it. Yes, test it well. Execute the developed test plan. Actually, figure out that you're going to test it in multiple circumstances. And you don't want to just test to the minimum requirements. You actually want to know how far till it breaks. I mean, you don't want to break your beautiful prototype, but you'd like to know that it isn't, that you can hold 35, but 35.1 and boom, it goes down, because the first shock you take, you know, you're gonna fall apart, it's gonna fall apart on you. So figure out what the actual margins are to where it breaks. Okay, next one. So let's talk about the solar powered scooter. If we're gonna see how far it exceeds the test plan, how would we do that? Burst it out, please, speak loudly. Huh. You got it. Go like 35, 40, 45. See where you stop. See where it fails to meet the other requirements. Next one. Speed. How do we exceed the test plan? Come on. Run it through a range of speeds. Up and down. You know, 12 kilometers per hour, 10, 15, 20. Where does it stop? What's the fastest this thing can go? Shade. How do we exceed the test plan in shade? you know, take it into this gym, ride it around, see how long it lasts. You know, maybe you find out it lasts way longer, like the Mars rovers. They were supposed to be there for 3 months, and what is 10 years later? That's exceeding performance specifications. And again, we're stressing all sorts of technical knowledge on these. Next one. All right, evaluate those test results. Did they satisfy the design criteria? And hopefully your first time around they didn't, something broke, and you've got to reevaluate. And so can you tweak the process? Tweak it rather than completely throwing it out and redesigning it. It's really, really smart to fail quickly, because you don't want to get to the very end and then fail, because now you've got a complete redesign with no schedule left to get this done. So fail quick, do your early testing, and keep testing on successive items so that you know that it's, you know, eventually you're going to get this thing tweaked up so that it's going to work. And this takes a while. Don't go to the last day before it's due and think you're going to start testing. Plan it out. Next. All right, so redesign examples. If the solar scooter can't move 35 kilograms, what do you do? Yeah. Yeah, take some weight off the scooter itself, because any weight that's off the scooter you can carry. Good. Others? Yeah. That's going to add weight to the scooter, but maybe you could put a bigger motor on it or better gear ratio. Okay, next. Okay, scooter speed only reaches 5 kilometers per hour. How do you make it go faster? Yeah, more power. Or you can lighten it up. So you know, higher RPM, wheel diameters, reduce the scooter weight. Next one. All right, so we're at the end. We've got a working prototype. So at this point now in your lab notebooks, you've got a complete record of all the key decisions. You've got good drawings, how it started and how it's evolved through time. You have test plans, what your initial test plan was, and elaborated at the end of, you know, how you actually tested it. Results, you know, did it work? Where was it weak? And conclusions, does this meet the specifications, and why and how? What would you do next differently if you had to do it over again? And lessons learned. And like I said, this is actually an important step, because at NASA, we do net lessons learned. I'm constantly going through the lessons learned databases for the Mars rovers to try to understand where they had failures and where we can improve ours. So it's really important to document these things. Next one, please. Avoid these pitfalls. Who cares if you don't have an end product that matters? Who cares? Why'd you build it anyway? If it's already been done before in the same form, why do it again? You want to make something better. Just analyzing things. We don't allow you to just analyze something. You actually have to build something. Gadgetry and kits, if you're just building a kit, I really don't care. You have to have some original content. And proceeding with testing without making sure that the end user approves of what you've built. This is called validation. Making sure that you've built the right product that meets the needs of the user. And don't do a demonstration project. You can go to the next one. Demonstration projects are generally something on the order of how something works. How does maglev trains work? We don't want you to tell us how something works. We just don't want you to build us a demonstration. We want you to actually improve an engineering prototype. So if you get something like this where, maybe you did how a maglev train works because you're interested in it, but can you do something like, can you make the maglev train go longer? Can you lighten it up? Can you increase the load on the maglev train? Those are engineering questions rather than just a demonstration. Yeah, no volcanoes, by the way. Playing with magnetic fields, whatever. If you're looking at transportation, I've seen a lot of projects on improving safety equipment, huge number of projects on alerting people when babies are left in the back seat, huge number of projects. Anyway, next. So in summary, next one down. So your project needs to meet a need and have a customer who actually cares about it, who wants it. Maybe your aunt can't keep track of all of her pills, so you design a pill bottle that alerts her when she needs the next medication. You have to have design criteria and constraints. It has to go 15 kilometers per hour at a minimum. Simple criteria. Or like our Lunar Rover, it has to last for at least 8 hours while drilling in a permanently shaded region. That's a design criteria. Evaluate your alternatives. Generate your test plan. Have fun, build a great prototype, build more than one, that'd be good. Evaluate them against your test plans, analyze them, tweak them. If you can help it, don't completely go through a redesign that's gonna set you way back. And make sure that you do your project book, take it with you to science fair, have it there on the table. Our judges love to read and understand the thought process you went through when you did your project. It should have your analyses, your decisions, specifications, and your results. Anyway, and most importantly, next slide, please, have fun with this. Engineering is, I've had a blast with my career over the years. I had no idea when I started at NASA at age 16 that it was going to turn into a consuming and fun career. I've worked in so many different fields, and it's just fantastic to get back and start on a project, another project on the moon. Anyway, so have fun and thank you. Any questions?
You did really good for time. I'm very.
I was trying to pull it in.